Finally, let's dive into satellite imagery and learn how to interpret the different types of satellite pictures you'll see in the field. Satellites are typically launched into two distinct types of orbits. We have geostationary and polar orbits. Both serve very different purposes, and each comes with its own unique set of advantages and limitations. Geostationary satellites sit about 36,000 kilometers above the equator, which allows them to maintain a fixed position relative to the Earth. The biggest advantage here is their impressive field of view, as they cover an entire third of the Earth's surface. Plus, you can stitch together a series of images from a geostationary satellite into a movie loop, which is perfect for tracking the development and movement of specific cloud features. Of course, they do come with a few drawbacks. Because their orbit is so high, the image resolution is typically lower compared to other types of satellites. Additionally, since they are locked over the equator, the Earth's curvature means they cannot provide any coverage over the polar regions. Polar orbiting satellites, on the other hand, operate at a much lower altitude between 600 and 1000 kilometers, which allows them to capture images with much higher resolution. They are excellent for viewing the polar regions and are sun-synchronous, meaning they cross the equator at the same local time every day. With each orbit, they shift westward by about 25 degrees, allowing them to complete roughly 14 orbits every 24 hours. However, polar orbiting satellite imagery has its own set of challenges. Because they are in a much lower orbit, their field of view is significantly narrower, and they won't pass over the same location again for another 12 hours. Consequently, you cannot use them to track the movement of individual cloud features. So, those are the two primary types of orbits, but remember, there are also various types of images captured by satellite sensors. We'll examine three of the most common and useful types for aviation, though keep in mind that many others exist. First, let's look at visible imagery. Think of this as the view you would see if you were actually sitting on the satellite. These sensors measure radiation in the 0.6 to 0.9 micrometer range, which corresponds to the visible light spectrum. The brightness you see in these images depends on the solar elevation, the viewing angle, the reflectivity of the surface, also known as its albedo, and the overall resolution of the image. Albedo is arguably our most critical factor, so let's set the others aside for a moment and focus our attention squarely on that. Think of a visible satellite image as a detailed map showcasing the reflectivity of the surface below. As a general rule, thick clouds are more reflective than thin ones, which is why they appear much brighter to us. Similarly, water clouds are more reflective than ice clouds, meaning they will also show up as brighter features on your display. Furthermore, clouds made up of smaller droplets are more reflective than those composed of larger droplets. This explains why fog appears remarkably bright on visible satellite imagery, even though it is physically quite thin. So, to summarize, on a visible satellite image, low reflectivity appears black, high reflectivity appears white, and various shades of gray represent everything in between. Most clouds show up clearly, but watch out for exceptions, like when the ground is covered in snow or ice, or when thin cirrus is viewed against a bright background like lower clouds. In these cases, the lack of contrast makes them tough to spot. Another essential tool is infrared imagery, which captures radiation in the 10.5 to 12.5 micrometer wavelength range. Interpreting infrared images is actually quite straightforward once you get the hang of it. You can simply think of the brightness levels as a direct indication of the temperature of the underlying surface. This gives us a huge advantage. We can monitor these images at any time of day, regardless of whether the sun is shining, unlike visible images which are limited to daylight hours. Essentially, in infrared imagery, the highest radiance comes from the warmest surfaces and appears black, while the lowest radiance comes from the coldest surfaces and appears white. Any intermediate radiances will show up in various shades of gray along that scale. This table provides a great guide on how to interpret both visible and infrared satellite images. When you use both image types together, it becomes incredibly powerful for identifying the locations of surface fronts, as well as upper-level ridges and troughs. This combined approach also helps us track the development stages of depressions and tropical cyclones, along with identifying specific cloud types. It is even possible to estimate the wind structure and atmospheric stability, detect the presence of lee waves, and map out the extent of snow cover or sea ice. With that foundation in place, let's dive into a few examples and see what we can uncover from these images. Here is a visible image captured by Meteosat, which is a geostationary satellite positioned directly over the equator above Africa. Let's jump right in and make a rough estimate of the current surface synoptic situation. You can see we have low-pressure centers located right here, here, and here. We are tracking a small frontal system near the low pressure over the southern UK, which includes a warm front, a cold front, and an occlusion. This system gets a bit more interesting because it's actually merging with a new one developing right here. Now, let's take a look at that same picture, but through the lens of the infrared channel. You'll notice the same features we spotted on the visible image, but it's much easier to identify another frontal system to the north that was a bit vague before. Another vital type of satellite imagery you'll want to get familiar with is the water vapor image. These images work by measuring radiance specifically in the 5.7 to 7.1 micrometer wavelength range. That's a specific region of the spectrum where water vapor absorbs energy quite strongly. Here's a quick tip: darker shades indicate a drier upper atmosphere, while lighter shading highlights areas with higher humidity levels. While water vapor images aren't always as crisp as other types of satellite imagery, they are incredibly useful. There are definitely moments where you'll see a very clear delineation between high and low humidity. One classic example is where moist air from a massive cumulonimbus cloud punches up into the drier stratospheric air. You'll typically see this occurring in the tropics. Another great example appears on the poleward side of the polar front jet, where moist, cirrus-laden air beneath the tropical tropopause meets the dry stratospheric air overlying the polar tropopause. So, looking at this water vapor image, we can pinpoint the exact position of the polar front jet right here. As you can see, satellite imagery offers us so much more than just a view of cloud structures. Meteorologists actually use these images to measure several other important parameters. For instance, we can derive wind data by tracking cloud movement across consecutive geostationary images. Also, by comparing the infrared image with the atmospheric temperature profile, we can calculate the temperature and therefore the altitude of those cloud tops. Moving right along, when we have clear skies with no cloud cover, we can actually calculate the sea surface temperature. Take a look at this specific image. What you are seeing here is sea ice. You might run into satellite pictures known as false color images from time to time. While they look different, they provide the exact same data as grayscale images, they just use color to make those details pop. And with that, we've wrapped up our look at remote sensing. The data gathered from these techniques is a fantastic tool, offering us a much clearer, more comprehensive picture